The broadcast is now starting. All attendees are in listen-only mode.
Good morning and good afternoon, everyone. Welcome to Razorleaf's Digital Thread webinar series. My name is Kristen Schloss, and we are excited to have you join us today for our fourth webinar in the series, Building a Foundation for Digital Twins. Today, we will demonstrate what building blocks are needed to bridge the gap between the physical and digital world. But before we begin, just a few housekeeping notes. First, this webinar will be recorded. We will be sharing this recording to all registrants. Also, during this webinar, we value your opinions and encourage any questions and feedback. To ask a question, please enter them into the panel at any time during this presentation. We will have a Q&A session at the conclusion of the presentation, and if we don't get to all the questions, we will ensure we get back to you as soon as possible. So I'm pleased to introduce you to our speakers today. First, Derek Meeting, who is our engagement director. He will be facilitating the discussion today. Derek has been with Razorleaf since it was founded over 20 years ago. Also, Jonathan Scott, who's our chief architect. He's our digital transformation evangelist, promoting the use of digital thread and digital twin concepts for decades. So on that note, I'm going to hand this over to Derek to start the presentation.
Kristen, thank you very much. Welcome, everyone. Welcome, Jonathan. Thanks for taking time to go over this with us. Let's just kind of talk about what got us here. This is the fourth in a series of webinars that Razorleaf has done on the digital thread and digital twin. You remember we started with a webinar about strengthening your digital thread with MBE. We talked about realizing the digital thread vision with PLM. And then last time we talked about 3 ways to get started with the digital thread journey. Hopefully you were able to join us on those webinars. If not, you can see them on demand on our website. So I encourage you to go take a look at those. As we go over today, we're going to kind of do a little bit of a review of some of the things we talked about in those previous webinars. We're going to then introduce you to the digital twin concepts and terminologies that are going to be important for the remainder of our discussion today. What variables come into play as you try to determine how to build a digital twin and what it should look like? We'll go through some real world examples, or at least one real world example of a digital twin from a client of ours. We'll talk about the benefits, then finally close about talking about some of the building blocks that are needed to realize a digital twin. We'll save some time at the end for questions and answers. So as Christian mentioned, if you have any questions, feel free to enter them in the chat window at any time during the presentation, and we'll take those questions at the end. So with that, let's turn it over to Jonathan. And Jonathan, if you could maybe kind of just start and do a little bit of that review that we talked about, talk about some of the things that we need to understand about digital thread in order to set the stage for digital twin.
Yeah, absolutely, Derek. Thank you. And let's jump in talking about digital thread. I'm going to recap something we talked about in previous webinars, like you mentioned. But our definition of digital thread is a set of connected records of the data and activities which define a product, or in some cases, process. Now, I'll fully admit throughout the whole presentation today, I have a bias toward thinking about product. So forgive me if every time we're talking about digital thread or digital twin, I'm thinking about the product aspects of it. But just know that it can also represent things that are a process, if that's what we're delivering. Perhaps we're delivering some kind of manufacturing or service process or things like that. But let's take this definition from the bottom up and kind of break it down, because that's what I think is useful in talking about a definition here. So whatever it is we're focused on, let's say product for a minute, it's the collection of data and activities about it, the things that define it, right? And when I say data and activities, I'm separating those because the data that defines a product is pretty straightforward, whether that's models, drawings, specifications, requirements. Those are all pieces of information that when you put them together in composite, define that product or that process. But the activities are maybe not as obvious. So the activities that give us that data can be just as important. So the project plans and tasks within those project plans that we execute that deliver on that data. How did we collect requirements from the customer? How did we define the different components? Did we use a supplier or a subcontractor? Those kinds of activities provide important context for the data. So that's also part of our digital thread, part of the information we need. And going up to the very first line here, the set of connected records of all of that. So the data and activities, we need those connected in a way that gives us context so that we understand, oh, that version of the drawing was generated from the product revision cycle that we went through after the product had been on the market 3 years. Oh, okay, well, that context is unique. That helps us understand something we wouldn't have seen another way. So the digital thread is about putting all of that together and connecting it. So we've got the data and the activities all connected so that we have a full context around the definition of a product or process. Let me just dive in and talk about what some of those pieces of a digital thread are so that you've got a little more practical understanding of what I mean when I say that. So this is, again, how Razorleaf thinks of this, or how we define it. There are folks who would say there are, elements I'm describing that are part of the digital thread which are not relevant for them. And there are other things that people would add in because of their industry. So this isn't meant to be a one-size-fits-all, but let me just talk through a couple of areas. We start frequently with requirements, and requirements traceability being part of the digital thread. So if we start by understanding what the product needs to do, or what the process needs to do, what it needs to meet, that's a great place to begin, to try and describe that and understand that data. That frequently then flows into systems engineering. Maybe you don't call it this, maybe you don't have this specific discipline within your organization, but when you start to take those requirements and imagine how you might address them with a product, imagine the concepts you might use and break those down into functions or features or logical components, that type of activity is important, and capturing that information is important. You may generate a lot of different information as you do that, and that brings me to this third one here, right? Product-related content. Who knows what that might be, and that can be quite fuzzy for a lot of organizations, but organizing it and connecting it into the thread is important. So then we get to some activities. When I talk about projects or change management processes, these are some of those activities that give this other data context. It actually gives all of the data throughout the rest of this some context, right? That you know when it was created, under what circumstances, was it early in the maturity of the product in the NPI process perhaps, or was it a late change in a reaction to the market, maybe an updated requirement? So these activities give us some of that context. The core of a lot of product definition are these next couple here: the BOM or product structure, the CAD data, drawings, technical definition, and then the configuration management that ties it all together, right? So what versions of what replaced, superseded when, obsoleted when, how are those all coming together to a different baseline of the product, and how's that baseline evolved over time? And of course, that all goes back to this context of change management. These are the activities that help shape and change that. Other elements of the digital thread could include analysis and simulation, right? Here I'm using a more formal term, MDAO, to represent any type of simulation and analysis that you might do, and even optimization of the product. Beyond just looking at the product itself and what those specifications are, parts of your digital thread may be the manufacturing definition, how it got made. Some industries that's critical, other industries it's less relevant how it got made, as long as it meets the product specs and conforms to those. And then lastly, if you are making lots and lots of your product, even if you're making just more than one, you need to know how the first one is different from the second one, is different from the third, is different from the 10,000th. But by tracking that and understanding it, you do connect it back to the specific pieces of data that you may need in other pieces of your digital thread. So that's just a quick recap of how we view digital thread and what digital thread is, because we're going to talk about that being a building block for what we need to discuss on digital twin.
Perfect, Jonathan. That's good, a review. So maybe let's do a similar thing with digital twin. Give us the definition of digital twin.
Sure. So again, this is Razorleaf's definition of digital twin. It's not going to align with what everybody out there says, but I think it's a good composite view. I believe the digital twin, and again, I mentioned it earlier, I'm kind of focused on product when I think of it, but it could represent process too. But it's a multifaceted digital model of a physical instance, right? Purposefully, I'm trying to keep this simple. You can add a lot of other details to it, but what I'm getting at is that a digital twin represents one specific physical instance of your product. So if you make 1,000 of them, you have 1,000 digital twins. You may have one long digital thread that represents all of that, but you're going to have unique digital twins for each of those 1,000 products that you make. It's a multifaceted digital model. Of course, it needs to be digital, right? Because it's a representation of your physical product that lives over in the computer world, right? But it's important that it's multifaceted. It's not just the CAD models of your product. It's not just the takt time model of your process, that sort of thing. There are a lot of different elements, and the digital twin brings all of those important facets together in one place and represents uniquely that physical instance. Let me dig into that point about models for a second, because it's very easy, and a lot of people, this is where their head goes immediately. It's very easy to think of CAD model, 3D model, geometry model, when we say a model. And certainly those are a very valuable model when we talk about digital twins. But my example here, I've got 6 different models of a motor on the screen. I've got one here that looks just like a CAD model, right? This is the geometry. Maybe it's a neutral file, but it's describing the geometry of my motor. This one I have here in the middle, this looks like it is some sort of analysis. It's maybe a simulation or a behavioral model of the motor, perhaps something thermal, right? It's hot here in the middle and cool on the ends, that kind of thing. So maybe it's a thermal model. What I've got here looks like a realistic rendering. So maybe this is a marketing type of model that I'm interested in. Down in the lower left, maybe this is a functional or a logical model, something that I'd use in schematics to describe how the motor behaves or how it fits into a system. I've got another simulation model here, just pointing out that maybe different domains within one type of model, a simulation model. Maybe this is electromagnetic modeling and this one's thermal. And here I've got maybe the simplest model of all. This is just a physics-based model of the angular position of the shaft based on, simple mechanics equations. That's also a model though, right? And note, this has nothing to do with geometry. When you really want to understand the behavior and have a digital twin, you need a composite of several of these. Maybe not all, maybe more than what I've shown here, but you need to put them all together to really have a digital twin.
So that does make sense. I think you're right. Most of our minds go to CAD model when we think model, but your explanation is fair, and that makes sense. I buy it that those are all models. Help us correlate these models then to a digital twin.
Sure. And it's interesting. It's a tricky thing, talking about twins, because there are a lot of terms that people use out there. I mentioned the different kinds of models. When you talk about digital twins, people are going to say digital twin and virtual twin and product twin and factory twin and all kinds of things. And some of that can seem a little bit academic in terms of an argument. It's, just the finer details and let's focus on what it's going to do for us. True, but the nomenclature can be important because of the questions behind it, right? Why are people trying to define the nomenclature? Why are they arguing over terms? The clarifying questions are relevant in terms of understanding what you're building and how it relates to the other things you might need. For example, does the twin that you're interested in exist before you've ever made any physical instances? Or does it exist after you've made one and it represents that physical instance? How many physical instances does it represent? Does it represent a whole batch of them, or all the ones you made in the month of February, or does it represent one specific physical instance? Does it represent a product or a process? I mentioned that earlier. That is going to have a lot of difference in what you call it. How does data flow between the digital side and the physical side? Does it flow from the physical to the digital and you just have this kind of model of your physical? Does it flow back from the digital world to the physical world and the digital thing is controlling the physical thing? And then finally, does it represent the work, the result, the thing you care about, the product maybe? Or does it represent the workshop, the process of getting there, or maybe not just the process of getting there, but all the tools and equipment and systems and maybe the whole factory used in delivering the product? So all of these kinds of questions are going to get us to some specific terms. And I want to take us through a few of them, and I'm going to highlight a couple of places where I think the differentiation terms matters. I'll leave this up and people can certainly read it later. But in these first couple, I want to differentiate the digital twin from the virtual twin. So in my view, the digital twin is related to a physical instance. So you have to have created some of your product, the physical instantiation of it, before you can have any digital twins, because there's one digital twin for each one that comes off the manufacturing line. The virtual twin, you could have that long before you ever make the first one. It's really a prototype, right? And so you notice my terms in parentheses here. I just want to give you some reference point. I am pulling some of that from the people that, in my view, really started this digital twin concept and talking about it, and that's NASA. I don't want to get into history lessons because I'm not any great student of the history of the digital twin concept, but I do believe NASA really pioneered a lot of these concepts, and they used terms like digital twin prototype, digital twin instance, and digital twin aggregate for a reason, right? Because they wanted to differentiate and talk about different things there. So I think it's important to note the difference between virtual twin and digital twin, even if you call them something different. I think that's a key differentiator. Another one is I want to make sure people are thinking about the difference between a digital model and a virtual twin, right? And I would differentiate those by saying the virtual twin is a composite. It's a holistic view. It's the multifaceted type of thing where you're looking at it from a lot of different domains to really represent your product, whereas digital model could be any one aspect of it. It could be very focused. Let me throw in another set of terms here to kind of complete some of the terminology that I think is important. I want to highlight the bottom two on the left, product twin and process twin. Really already touched on that, but I think it is important to differentiate because I always think of product twin first, but there are a lot of folks who think of process twin first. And if you're not clear about it when you're speaking to people, you could be on a totally different page and not even realize it. I also want to talk about those bottom three. How do process twin and product twin come together for something that a lot of people are talking about actively now, a digital factory twin? So I think a digital factory twin is a combination of all of the digital product twins of all the equipment in your factory, along with the digital process twins of how that equipment behaves, how it operates, what work it performs, how those come together in a more complex system of processes. All of that together is what you need to build a twin of your digital factory. It's pretty heady. That's a pretty big deal, but there are a lot of people who are talking about this now. Other terms that are worth just knowing that people are talking about: digital shadow, digital surrogate, digital generator. A lot of that has to do with the flow of information between the physical and the digital world and giving labels to those. So I'm not personally, a real stickler for a lot of this, but I think it is important to remember that there are different concepts here, regardless of what you call them. So what I'd like to do from here, Derek, is I want to take this and put this in the context of kind of a nominal product life cycle, right? So we work with a lot of different industries, and there's a lot that's different about those. There's a lot that's in common too. So I'm going to give you kind of a product life cycle view of developing, building, delivering, using, servicing a product, and how some of these terms fit into that, I think, right? So I'm going to use the model-based paradigm of that, but let's just walk through that life cycle. So I think in product development, we start from the voice of the customer all the way at the far left. And from that, we try and understand what they want and translate that into the requirements that we need. If we're being robust about this, really, this is the model-based systems engineering discipline. It's collecting and understanding the requirements, making them granular, making them accurate, subdividing them, deriving them, breaking them down, then developing functional and logical models based on those so we can get to a physical product design or multiples and do some trade studies across them. But that's that whole MBSE discipline that we start with. From there, we move into the different design disciplines or domains potentially. Maybe our product is mechanical only, but if it's got multiple disciplines or domains within the product design, maybe there's an electrical model or a software model, but that's all the MBD area, right? And from there, we move into engineering. Now, there's, of course, engineering created related throughout this, but let's just add that on as the next layer and say the simulation, the analysis, the calculations, all the things that validate that the design is satisfying the requirements is what we think of as model-based engineering. And when we put all of that together in an integrated model, right? And so we've got that electromechanical with code type of model with some of the basic behavioral simulations and things like that. I would call that the virtual product twin, right? So that's where I think this fits. Over in product development, before we've ever made the first one of these, we have a virtual product twin. Well, our next logical step, though, is to think about making it, right? So when we start to think about moving from the product development area over to the factory area, before we actually get into making anything, we do need to plan it. So there's manufacturing and quality things, right? And there's some model-based takes on these that are important to consider that go together to make that virtual process twin. What is the process of how we build our product, right? How do we make the individual components, or how do we source and buy them? How do we assemble them, put them together? How do we test them, assure that they meet the specifications? That's all part of our virtual process twin. All right, now when we've got a plan for the product and a plan for the process of how to build the product, it's time to make it, right? So at physical instantiation, that's the point where we shift over and we're in the factory now making the individual physical instances, those units, right? So unit 1 rolls off the line, unit 2 rolls off the line, unit 3 rolls off the line, until the point where we're starting to deliver these to the customer. Now, I want to mention something about what happens as we're building these. So we had a plan with the virtual process twin, but as we execute that and we use imperfect equipment, or we use one set of equipment in one plant and a different set in another, and some things happen differently on a Monday than they do on a Friday, and maybe our autoclave has a different bake temperature for that composite that we're making. The data that we collect from our plant, from our factory, is important to each of those units, right? So they're built differently on different days of the week. Maybe they're a little bit unique. That's going to matter to us later. So collecting that sensor data, what a lot of people would talk about is industrial Internet of Things data, right? Coming from the sensors off of the machines and the equipment in our plant. That is important to understanding our digital factory twin, right? It's a composite of all the equipment we have, all the processes we're running, our digital perspective of that, but also with the real-time data collected as we've made these different units. All right, let's keep going though. As those products are delivered and they go out into the field, right? Unit 1 and Unit 2, they make it out there and they're being used by customers. Let's take the example of Unit 3, which is out there being used, but then needs some maintenance, some service event, some repair, something like that. So this starts to bring in not only the field area, the products being used in the field, but also the service component when they have to come back in to have some work done on them. There's another area where we have some planning that we need to do, this model-based sustainment activity that would tell us what kind of service we do and get our unit back into the field. But as we look at all of this, we say, okay, there's something else sensor-wise, data-wise that matters. So those little sensor icons, yeah, we collected information when it was in the factory, but we're also collecting sensor data when the products are out being used by customers. Now, how many hours a day is it being used? What kind of vibration is it undergoing? All that sensor data is the Internet of Things, so just the regular IoT. When we put all of this together, this is what gets us to the digital twin, right? So if I look at Unit 1 specifically, and I trace back to exactly how it was made, what were the temperature settings on the heat treat machine and that sort of thing in the factory, as well as what are the sensors telling me today when it's used in the field, that IoT data. And all of that traces back to the virtual product twin that made it, exactly how it was configured when it was made that day. And let me throw in one more thing. If we were talking about Unit 3, any repairs or changes or modifications that happened, that whole history is the digital twin, right? All that information comes together to make a digital twin for us. Hopefully that helps.
Jonathan, that's a great, yeah, that's a great explanation. I liked your introduction of this kind of originating at NASA. However, I'll argue that this is a very robust and comprehensive life cycle of a digital twin. I can absolutely see why NASA wouldn't want something like this, but it doesn't It doesn't take a rocket scientist to figure out that the digital twin for a interplanetary rover is probably different than the one for a refrigerator. So what sort of variables do you consider when you start talking about what does my digital twin look like?
Yeah, that's a great point, Derek, right? Because not everybody has a spacecraft, and not everybody needs that level of detail, or even are those things necessarily relevant. So let's dive into that for a minute and talk about how digital twins can be different and should be different from customer to customer. So we talked about digital twins being unique to the specific product instance, right, that comes off the line. But let's talk about uniqueness in a different sense. My type of digital twin that my business builds is very different from the type that your business builds. And that could be because we're in different industries, right? That's one thing that could factor into it. For example, the level of regulation if I'm making aircraft is very different than if I'm making light bulbs, right? So there may be things about my twin that are important when I'm making an airplane that I would never even consider putting into my light bulb digital twin. What about the product lifespan? I'll keep going with my light bulb and my aircraft. One's around for 30 to 50 years and the other might last 2 years. So given that, I'm going to put the different level of effort into it. I'm going to look for different things. All of those are going to matter. What about the amount of hardware versus software? That's also going to change what my twin might look like. If I have zero software, that's a different looking twin than if I've got tons of software that can maybe change over time. And then lastly, let's talk about privacy for a minute too. These are things that you wouldn't necessarily think of immediately, but if I am selling a piece of capital equipment into a customer and they're going to use it and they want great uptime out of it, they really don't care if I do tons of monitoring and I collect a huge data stream so that I can help keep their equipment up and running. But if you're selling me a baby monitor or a toothbrush or maybe even a car, I may have some concerns about how much of my data you're capturing. Are you watching the GPS on my car? That might be very relevant if you're trying to help me maintain it, but I might not like that. So these are all things that can matter about the digital twin. How about from another angle? Let's talk about the tools, right? Depending on your industry and just your business, maybe even if you held the industry constant, in your business, maybe you do systems engineering. Maybe you don't. That can make a big difference as to whether that goes into your twin or not. And maybe you don't do it today, but you want to do it tomorrow. That's another thing that could matter. What about the domains of design software that you use? Do you have electrical parts of your design and software, or is it just mechanical, or is it sheerly an electrical product? Or maybe it's a software-only product. What about simulations, right? I mentioned earlier when we talked about models, a thermal domain and an electromagnetic domain. Well, okay, what if you've got fluid flow? But what if you don't? What if your product has nothing to do with any of those things? Your twin's going to be quite different than someone who does. How about manufacturing? I mentioned this earlier, but it's very true. There are industries I know of that we've worked with that they care so much about the process of manufacturing the product, they actually consider that part of their configuration management. They change the manufacturing process, they want to rev their product. That's a little bit of a mind blower for me. But that's very different from another industry who says, look, I don't care where I make it. I can make it in Mexico, I can make it in the US, in Europe, Asia, wherever, as long as it meets the product specs, it doesn't matter. So they don't care about manufacturing simulation. And how about sensor data that you're going to collect as part of the manufacturing process, or maybe as part of the IoT of it later? Maybe you have no sensors on your product. Maybe you have 1,000 sensors on your product. That will also matter. How about fidelity, right? The accuracy that you need out of your digital twin can make a big difference in what you build here. There are people who think of materials as just homogeneous things. It's kind of a general chemical compound. It's, aluminum 6061 T6. Then there are people who look at materials at a molecular level. They want to know about grain boundaries. They want to know about cure times. They want lots of detail. Same thing with geometry. People who care a lot about geometry and tight tolerances and things like that, and others who, as long as it's within the operating parameters, it's fine. Same thing with sensors, right? What kind of sensor data do I get back? I mentioned this already in tools and technologies, but a little different angle here. Let's say I'm collecting one data point every minute, right? And my product's going to be out in the field for 2 years. That's a lot of data for just one sensor. Do I summarize it? Do I collect it all? How do I use it? Do I look at it in aggregate across multiple digital twins? And then what about the scientific maturity of the principles on which my product is based? There are lots of things where we've known the science and the engineering and we get it and it's been around for 100 years. But there are also areas where we have products where we're still understanding the science. And when we don't fully understand the science or don't have it all nailed down, our simulations, our predictions, the fidelity isn't quite as good. So lots of those things will also matter. Last category here, what's the purpose of your twin? That has a huge influence over what it might look like. For example, if you're just trying to optimize the performance of your product, so your twin is meant to look at how people use it in the field, and that feeds back into new product development. That's one thing. But what if you're not selling your product as a product anymore? Now you're selling it as a service. So, you sell power by the hour for your engines like they do on some aircraft, or you're selling your equipment uptime. If that's the case, then the purpose of your digital twin is to maximize that uptime and availability. You might be looking at some different things, trying to track some different sensors that can all matter. What if it's as simple as I just need to ensure safety, right? I just need shutdowns and things like that. I need to watch for a couple of key parameters. Again, that'll adjust what you're interested in. Another possibility here that a lot of people are doing with their digital twins is to try and control the physical instance. So I'm constantly tuning, I'm constantly optimizing the performance, right? Think about self-driving cars as an example, right? So we have a digital twin of the vehicle, we're collecting lots of data in aggregate, and then we're updating the software on those cars because what we're trying to do is control the physical car using our digital models of how it's going to behave. That's sort of a different animal. You can see how it's not likely that any two digital twins are going to be the same, even with competitors in the same industry, because of all these variables. I think that really, sort of is mind-blowing to me, Derek.
Yeah, that was great. So let's see if we can't go through a real-world scenario of a customer of ours that had some of these variables in front of them and then had to build their digital twin. Tell us what that looked like.
Absolutely. So I love this example. This is a very interesting customer to work with, and I'll just sort of set the table here a bit on their industry. This was a defense customer. They're the end customer of a piece of equipment, a weapons platform. The challenge that they had is, they've had plenty of weapons platforms in the past, and what they sort of suffer through is these things are complicated machines in really harsh environments, and they break, and it's hard to keep them up and running. And the way that defense can run is you got people changing in and out, and different operators and pilots, and lots of variables change, so it's tough to keep the thing up and running. It's tough to know exactly even what parts are on the truck or the helicopter or ship that you are working with, right? Who changed what out. Now there are logbooks and things like that, but things are not always up to date and instantaneous. How do I repair a certain thing? Oh, is that in this manual? Oh, I've got an updated part on it that doesn't work anymore. What about predictive maintenance? Maybe I don't even have any sensor data that would help me predict. All I can do is just bring it in every 30,000 miles as needed. So they're looking for a step change in readiness of a weapons platform, but how do they do it? And the solution is, well, you need a digital twin that helps you do that. And for them, that looked like a digital configuration management tool that was based on a PLM system so that they could know exactly what parts we're dealing with on which aircraft, on which truck, on which whatever piece of equipment, connected to a data warehouse that they were building separately that would collect that performance data for a particular tail number, a particular VIN number, right? That they'd say, all right, well, that one's running hot, or that one's been in service, or whatever. They could know the performance of a particular unit. What they were going for here is an increasingly accurate model of that particular instance that was connected to performance data so that they could solve the challenges I mentioned on the left. So what I want to take you through is, how did we help with that, right? How did we get to a digital twin that was useful and meaningful for them? What did they build? So let's start here. The first challenge they had is they were the customer of this design, not the people designing the product. So they started with very little data. I mean, they had specified requirements, right? I'm not showing that, but off to the left here, before they ever had a bill of material and CAD models and drawings, things like that, they had some requirements. But based on those, they needed to go collect all of this information from the OEM, right? From the system integrator that was offering to build, design and build the platform for them. But not only that, that systems integrator had information from suppliers they bought components from, radios, guidance systems, tires, all kinds of things that came from another supplier. So those details weren't actually shared with the OEM. So the OEM didn't know all this. They just knew kind of the envelopes, the interface, and things like that. So this customer needed to get the data from the OEM as well as from the supplier and integrate all of that together to get that holistic virtual twin, right? But the other challenge, of course, is they weren't in charge of all of the product development. So as things changed, they also needed to keep up with the changes, the new data, the added models, all of that, so that the virtual twin could evolve as they went. Okay, the next challenge then is, well, not only is the OEM doing that, right? Not only is the supplier doing that, and you got to keep up with that evolving data, but they're starting to deliver product, right? So when I get the first one that comes in for delivery and I look at it, I say, oh, well, all the changes I made in the last 2 weeks aren't applied. So I've got more virtual twin data than maybe I need, and I need to correlate my first physical delivery to, well, what was the configuration of the product when I received it? What data set applies to it uniquely, right? And then I've got changes I might have made once I received it. Now I need to make a change to it based on, I banged a tow truck into it sitting on the flight line. I needed to repair a part. All right, so I did this. Now this is unique to that one particular tail number of that aircraft. So it's different than the nominal baseline, right? So the as maintained is a little different. Well, when that's the case, now I need to think about those service bulletins that might come in to implement the changes I mentioned that were happening late in the game. So I've got to figure out how that then applies. So there's a lot of configuration control to keeping accurate status accounting of that truck or that aircraft or that ship, whatever it is, over time. All right, now let's put the performance piece into it. So let's assume we can do all that. And we did. We put the tools in place so that they could receive this data and configuration control this data and have that accurate, up-to-the-date baseline of the product. So now that we're connected, though, to performance data, we might get an alert, right? And it's not necessarily a bad alert like something's broken. It's just a system anomaly. Maybe it's just a sensor-based alert. It's over a threshold. Maybe it's AI monitoring. Hey, this one is performing out of bounds over what we would expect, or it's just some performance variance. We can't get to maximum RPM on that rotor, and we're not sure why. But whatever that anomaly is, what that would prompt them to do is go analyze. This is why they wanted to have that twin. They wanted to be able to go do an analysis, right? Get their digital twin and run some simulation and check to determine, all right, what's the outcome here? Is it going to be premature failure? Is it going to last for another 20,000 cycles? That's why we want to have the twin, so we can simulate it. And we needed to look at this specific tail number or VIN number, right? Not the one that's been a hangar queen sitting off in a hangar for the last 6 months. So with this step, they were able to have more predictive information about what they should do next to increase that availability. So last thing I'll talk about capability-wise that they wanted is, once that happened, they knew they would need to put together technical data packages to get a repair done, to buy spare parts, to buy replacement parts, to do an upgrade. So my fictional scenario here, let's say they analyzed it and they found that this component was going to fail. They wanted to quickly be able to get neutral, right? I got a PDF here, a neutral technical data set that was pulled from that specific digital twin, or perhaps from a virtual twin, either way, so that they could quickly get quotes, updates, designs, repairs, things like that. So that's just a sort of a picture of what they wanted to do, what they felt like they needed to do. Very purpose-built digital twin there.
That makes a lot of sense, Jonathan, and that really does help to underscore that thought about there's variables, some that are in your control, some that are out of your control, that play into what your digital twin looks like. So that's a good example. Now, even though digital twins look different across industries, companies, and whatnot, there's benefits that are common. Would you agree? What are some of those benefits that are common regardless of the fidelity of your digital twin?
I think that's right, Derek. I think you can put some of these benefits into pretty big buckets, and they are pretty common. Like you said, with the different types of twins and all the variables, there may be things that are unique to a certain circumstance or a certain industry or company, but some general digital twin benefits that I would highlight for people, these are going to look very similar to some benefits of a digital thread. I would also note they are different, right? Because once you build upon the digital thread and you have a unique digital twin for each physical instance, you get some very specific types of benefits out of that. But in general, I think decision support is one big benefit of having digital twins of the product. So the if I had only known, that digital twin is that knowledge base about a specific product instance. You know, take a maintenance guy, for example. Well, is there something wrong with the product? I see it's this panel here I need to fix. I'm going to go ahead and grind it down and build up some material on it, paint it, finish it, and it'll be good. Well, it turns out that panel's been repaired 3 times already, and it's too thin to do that kind of repair. But if you didn't know that, you would start working on it, you would destroy the piece, you'd have to order a replacement part, and you got a mess on your hands. If I had only known, I could make a different decision, is the point. So the more information you have that is relevant, accurate, and in the context of the specific one you're looking at, the better decisions you're going to make. And that decision support is a really important benefit. Now, maybe my example that I gave was trivial, but you can imagine all the decisions that get made about products every day between the OEM, the person who made the product, the customer, the person who uses it, the person who services it. That kind of decision support can have a lot of economic impact, and it's a huge benefit of digital twins. Another is the ability to automate to get new information, right? So my decision support is sort of about looking back at the record of what you have to support decisions. But sometimes you need to run the what if analysis. Can it take this? Should I shut this down? What should I do with the product next? When does it need to come in for maintenance? All of those questions, you may not have the information to answer them based on the historical data you have about your digital twin, but the ability to quickly automate answering those questions and what ifs is really beneficial. So let me give you an example. Here at the bottom, I show this equation. If you take the design models, and by the way, you need the specific exact design models used for this one VIN number or tail number, right? So not just the virtual twin, but you need the exact ones for the one you care about. Plus their as maintained state, right? So, what kind of parameters were used when this part was made on that specific date or lot code, and how has it been subjected to radiation or heat or whatever over time, plus the current conditions that you want to operate in. Oh, I'm going to go put it in, Himalayan cold or desert heat or whatever it might be, and I'm going to run it for 10,000 cycles. When you put all of this together, you get an accurate prediction. Now, assuming a good simulation model too, right? That we understand the physics and that kind of thing. But you're able to get an accurate prediction. And by automating that, right, making that quickly available, suddenly you're asking questions to the knowledge machine that is the digital twin, and that's a huge benefit. If you can trust the answers you get out of that and you can get those answers quickly without it costing you a lot when you ask the question, a lot of time, a lot of money, then that's a huge benefit. Let me talk about the last one here. Sometimes we need to do a look back that isn't about necessarily decision support, but it can relate to decisions you need to make. It can relate to automations and scenarios you need to check out. But sometimes we need to understand what's happened. Now, I talked about this as a digital thread benefit also, and it certainly is. Let's say you've got a problem where you unknowingly put lead paint on your toy that you're making for children, and you know that's a bad thing, but the next thing you need to figure out is, okay, how big of a problem is it? How widespread of a problem is it? That sort of thing. Your digital thread can help you with that root cause analysis and that impact analysis, right? Because you're looking at it generically across your product design. But your digital twins can help you even further. If you need to diagnose exactly which ones have the problem, where they are, whether they're being used, whether they're in service. You can automate a recall on them. The digital twin gives you this forensic capability to a whole different level, right? Much deeper that you can go. You can also start to look at things like, how does this twin compare with the aggregate of my other twins? Oh, are its performance, is its performance data out of range, out of nominal when I compare to others? That's the kind of thing you can do when you're looking at unique physical instances and you have digital twins to compare instead of just the normal digital thread of your overall product design. So there are a lot of benefits that you can get from a digital twin in these areas I'm talking about that are a little different, a little bit beyond what you can get just with a digital thread. But these are kind of the big buckets I would put it in, Derek.
Perfect. Yeah, that's good. So let's kind of put a bow on this and answer that question we started off at the beginning, which is, what are the building blocks to get there? And so I'm going to ask you to talk a little bit about some of those digital twin building blocks, and I'm going to throw a challenge at you and ask you to do it in about 3 minutes.
Ha! Good luck. Sorry, Derek. Let me try, though. Let's talk about those building blocks. I think I've touched on it many times in the call already, that the digital twin is built on a solid digital thread. So quickly going through an example that I used in a previous webinar, a strong digital thread might look like this for a product that, let's say it's a battery powered product. We've got some requirements for the product. The one I'm highlighting here is that it needs to operate at less than 170 degrees Fahrenheit. So these are data-driven, parameterized requirements, right? Very model-centric. That might drive us to a particular design, and here's our breakdown of our bill of material and our product structure, and that, of course, relates to mechanical models, electrical models, different domain models that I might have. Those, of course, feed into a simulation I might do, a thermal simulation. You can see that's connecting back to the 170 degrees. Maybe in my thermal simulation, I have some virtual sensors, right, that feed into my validation test plan, that I check that surface temperature, right? My next animation here. There we go. That surface temperature that connects back to the requirement that it doesn't exceed 170 degrees Fahrenheit, right? So that's my validation check that helps me close the loop using my digital thread, right? You see how the thread here runs from the requirement to the part, to the model, to the simulation, to the test, back to the requirement, so that I've got the feedback loop. When I was doing design, if it turns out that this was going to be a surface temp higher than 170, well, I would revise the design. I'd come back through this and I would check it out again until I had a product that could meet these requirements. Okay, that's all great. That's the virtual twin. That's what I planned for my product. But that is the foundation for digital twins. Because when I've got this nice, robust digital thread up here and a good virtual twin of my product, but I start thinking about serial number 79, the serial number 80 and 81, all these products out in the field, right, that are connected back to this. And I'm not showing the complication here, but maybe 82 is a little different. It uses a slightly different configuration here than 79 did. But so we got to be able to keep track of all of that, how it ties back to the different data sets. But let's look at what happens when these products down here are operating in the field and why this digital thread is such an important piece of that foundation. All right, so let's say they're all off and running, right? So 79's running, 80's running, each of our serial numbers is out running in the field, but there's a problem with serial number 85, right? So that digital twin for serial number 85 is telling me there's an issue. Well, how does it know there's an issue? This is why that robust digital thread is important as a foundation. That alert that I'm getting is because it maybe goes right back to the requirements, the operating parameters that I defined for it initially. And then what do I do with that? Let's say I've got an alert. Doesn't mean there's a problem, but maybe there's going to be a problem, and that's why this requirement was set. So I need to run an analysis. I need to use my simulation that I had based on my specific configuration, not just the virtual twin, but what serial number 85 looked like, so that I could come back with a result. And maybe my digital twin here is supposed to control my products in the field, but I can come back and tell, you know what, if that thing's going to be over temperature, given how long this serial number typically runs, that's going to cause a failure. So right now, I better go ahead and shut this down. So my digital twin is going to exercise some control over my physical twin. And you can see how the digital thread was a really key component of that. If I didn't have all of this, if I didn't have the requirements up front parameterized so that I could use them as part of my alerts, if I didn't have the simulation that I could plug in and feed in the specific configuration of my product to determine that analysis to make that decision, well, I wouldn't have done it. This thing might have just failed in the field. What's the outcome there? Maybe it's just an economic loss. Maybe it's a loss of life. Maybe it's a safety issue. I don't know. But we can see how it's really important and how that digital thread serves as that foundation. So I know I'm over time, Derek. Bear with me 1 minute. Let me tell you about what I think the typical building blocks are. I said digital thread is important, and I believe it is. There are a couple of pieces to that I want to highlight. I'm going to just build this out quickly and point out you need PLM tools. I don't mean a PLM system, right? A PLM system is part of this, don't get me wrong, but I mean all the PLM tools, things that help you track requirements and model your system from a systems engineering perspective, and 3D models, geometry models, other types of models, as well as process simulation tools. How does it behave? And then configuration management. How do you keep all of this together with the right versions of things, the right baselines, so that there's integrity to your data? So you need all of this, but they are, of course, industry appropriate, different and unique for every industry. So you got to pick what's right for you. But you also need unit and instance tracking. So it's great if you have all that, but it's sort of virtual twinish if you don't have unit and instance tracking. So you need to be able to differentiate which version of the product and how it ties back to a specific baseline. And you also need sensor data, the relevant sensor data, right? People are getting tripped up in this a lot today with, put all the sensors in the world on things. And what do I do with all that data? How's that helping me? You have to carefully plan what you need coming back to you from your factory and from the field to be useful to you. And then lastly, you need to find a way to tie all of that together. So if you look at these circles, I'll start from the left and say, this here is PLM, this is ERP, this is IoT, or maybe MES and IoT somewhere in here, depending on the sensor data you're talking about. But these kind of pillar systems within a lot of businesses are great, and they can operate on their own and share a little bit of data. But the instant you want a digital twin that is a picture of your unique physical instance, you better have some glue, right? Integration, orchestration tools that tie these together in a way that give you that digital twin type of output that you want. So I think those are all the key building blocks, Derek, that I would point to. Hopefully, not too far over there.
No, that was perfect, and that was a nice wrap up of what we talked about. So we appreciate everyone following along as we went through this. I hope that you were able to learn some stuff about digital twin, really how digital thread kind of provides the foundation for that digital twin, some of the variables that need to be taken into consideration, and then the benefits that someone would get as they start to build that digital twin. We do still have a few minutes left for questions, so Kristen, can I throw it back to you and see if there's any questions that have come in?
Yes, thank you, Derek and Jonathan. That was very informative. I do have a question from Omar, and he asks it in a couple parts. He wants to know if we have any experience in digital twins for mining environments. There's concern the time of implementation of a digital twin project, for example, related to the reliability of the mining process, since there's so many different steps in the mining process.
Yeah, so I'll tackle that one if you don't mind there, Derek. I think that I won't say I've got specific experience in the mining industry with digital twins. Now, I've worked with a couple of mining equipment makers over the years in the PLM space. But Omar, to your question, I do think that digital twins, if we see the relevance and the business benefit, there's always a way to start quickly and to start small and grow it out from that, because all this should be led by a business need. So to your point about the mining process being a multi-step process and there's a lot to it, and is it going to take us a long time to build a digital twin? Absolutely. For full fidelity and covering every base that you have and everything that you want, it may take quite a while. But could you start with a systems model? Could you make it product instance specific if you needed to give you the kind of results that you need, even if they're a little bit rough to start with, and then refine and iterate, right? So that's how I suggest people think about this. When you think about those building blocks, what do you need to get started to give you some value, and then work out from there.
Thank you, Jonathan. The next question I have is Robin asks, the merits of digital twin are fairly clear, but how are people justifying the cost of implementing the systems that build these digital twins?
That's a similar question, Jonathan. Why don't you continue that thought with that question in mind?
Yeah, it is a great point. And I think it does tie to what I was just saying, Derek, which is, think about the business benefit and build out from there, target exactly what you need. But let me turn it around a little bit and say, you've got in mind some digital twin that you're going to need 3 years from now. I know my industry is going to product as a service, and so that's how I'm going to have to be offering my product. So I need a digital twin. Okay, we'll start with the end in mind, right? I'm stealing from Stephen Covey there. Where do you need to be, and how are you going to get there? How are you going to build out to that? I suggest that people look at the steps they need to get to that full digital twin, whatever full digital twin is for them in the future, and think about how each step can provide some benefit. We talked about this a little bit on one of our digital thread webinars about strengthen your digital thread and build it out in the areas that are going to provide you value, right? So you can a lot of times think about that as, well, here's where I am, here's where I want to be, do that gap analysis, what are the steps to get there, and then try and order those steps so that there's some value each step along the way. So it's not asking for $30 million to create the systems to build digital twins. It's asking for $1 million this year and $1 million next year, but those are each for a certain benefit. And then maybe at some point it builds up to the overall price tag. And not that it always has to be $1 million either, but I think that's how I think of it is, build it piece by piece incrementally where you're getting value each step. Derek, would you add to that?
Yeah, no, I think you're right. And I think we can't forget the points that you made also about that there's different levels of digital twin that are important based on industry, based on product line, based on our consumer base. And so, the cost of implementing that should have some correlation to the cost of your product. The digital twin, to your point earlier, of a light bulb is not nearly going to be as robust as the digital twin of a jet engine. And so, we have to be able to look at that because that's going to start to, I think, drive how far we go. Initially, simple things. Those simple things start to provide business value, start to provide higher quality and better products. And that serves as the springboard to make that digital twin even more robust. And so let the successes of the things that we build in the first phases be the things that push us into the next phases.
Great, thanks, Jonathan and Derek. I know we're at the top of the hour. Just one more question and we'll wrap this up. Arjan asks, how AI and digital twins are integrated?
Great question. It's a good thing we've got another hour to talk. Oh, wait. I think the short answer is people are doing things in very specific areas with this. I can't speak to a lot of detail that I've seen a lot of places where they are integrated, but I certainly understand the use cases where this makes sense, right? Can I do pattern recognition for predictive analysis of a digital twin? Can I learn something looking at one digital twin that I apply to the rest of my fleet? Where AI can start to provide benefits once you have this really nice ordered data set. There's some interesting questions around how you incorporate what I'll say is the simulation, the predictive data that you could get out of simulation tools and correlate it to the actual data that you get to create a feedback loop there. So I think there are a lot of opportunities related to AI and digital twins, but I can't tell you that I've got a concrete use case that I've seen a customer apply yet where they're integrating them and then here's what they're doing it for. So I don't have a good concrete answer for you, but I think that there's a lot of relevance between those two topics.
Well, and one thing that's clear, Jonathan, is in order to allow the AI engines to do what they do, we have to feed them with data. And that data can either come from that virtual twin, or it can come from the actual digital twin. Coming from the digital twin, it's going to be more complete and more accurate. But at the end of the day, we've got to have data to feed into that AI engine, and digital twin is going to be critical to get that data.
Yeah, agreed.
Great, thank you both. Well, this covers our Q&A session, so thank you everyone for your participation. They're great questions. Any questions that we did not answer today, we will ensure that Derek or Jonathan reach out to you. Just to close out, I wanted to quickly point out a few things. Derek and Jonathan have mentioned to reach out to them to help for any help that you need to get started, so give them a call or email. Also, we have a self-diagnosis assessment to find out where you land in the digital thread maturity. It takes about 10 minutes, so I encourage you to check it out on our website. We will be following up with some technical tips and emails that you may find helpful in your digital thread journey. As Derek mentioned earlier, if you have missed previous webinars, we do have them available on demand on our website. And lastly, if you haven't signed up for our newsletter, we recommend that you do so, as there's a lot of great content on our blogs, and we summarize that in our bi-monthly newsletter. I want to thank Jonathan and Derek for a great presentation today. It was very interesting and informative. And most importantly, I want to thank all the attendees for your time and participation today. And I hope you have a great afternoon. Thank you.